So chapter 9 was looking at physical changes in matter. We spent chapters 6, 7, and 8 really focusing on chemical changes, chemical equations, reactions, stoichiometry, and the latter chapters of this second sort of unit or grouping of chapters that we looked at this year was focused on physical changes in matter, which are changes in which matter undergoes that does not change the composition of the substance, does not change the identity of the substance. So in chapter 9, the changes we were really looking at were phase changes and temperature changes, absorbing heat, releasing heat, making particles move faster, making particles move slower, making particles move further apart or closer together, but not breaking bonds, not changing what the actual substance is. So we introduced the idea of heat energy and looking at the difference between heat and temperature. Heat is a form of energy that is transferred between objects of differing temperature. Temperature is a measure of average kinetic energy of particles. So temperature is our way to measure if heat's being absorbed or released. Heat cannot be measured directly. There is no heatometer, right? We can't stick something in a substance and say, it's releasing this many joules of heat or absorbing this many joules or calories of heat. But the really subtle difference between heat and temperature is that heat is energy that's transferred from one object to another based on a difference in temperature, where temperature has to do with the average kinetic energy or the motions of the particles. We looked at heat transfer and defining heat transfer as endothermic versus exothermic. We separated the system versus surroundings as a way that we can all sort of commonly talk about heat transfer. The system is what we focus on. The surroundings is everything else. And the system and surroundings together make up the entire universe. We always define heat transfer from the perspective of the system. So if heat is leaving the system, like in that first beaker there, we consider that an exothermic reaction or an exothermic change, right? Heat's leaving or exiting the system into the surroundings. And if heat's going into the system, then we classify that as an endothermic change. We should be able to understand whether the heat transfer is endothermic or exothermic with respect to whatever the system is, and understand how the temperature is going to change with both the system and surroundings if heat's leaving or if heat's being absorbed. Eventually, heat will stop transferring once the substances come to thermal equilibrium. So if I have two substances, one at a higher temperature, the particles on average are moving faster, and one at a lower temperature where the particles on average are moving slower, heat will start to transfer. And what that transfer looks like on the particle level is these molecules will collide with these and transfer some of their energy to them. The faster moving particles will slow down as they give up some of their energy to the slower moving particles. The slower moving particles will speed up as they absorb some energy from the faster moving particles. The faster moving particles start to slow down. The slower particles start to speed up, and eventually they will come to some common average kinetic energy, so their temperature will be the same. And that's when heat stops flowing, when they reach a thermal equilibrium somewhere between the two temperatures of the highest temperature object and the lowest temperature object. We looked at quantifying heat transfer. Instead of just saying it's endothermic or exothermic, how many calories of heat or how many joules of heat were released by an object or absorbed? We can quantify heat mainly with those two units, joules and calories. And the equation we use is Q is equal to mc delta T. Q stands for the heat that's absorbed or released by the substance. M stands for the mass. C is the specific heat of the substance, and delta T is the change in temperature. So the amount of heat or the quantity of heat that something releases or absorbs depends on the mass of the substance, by how many degrees we're changing the temperature, and the specific heat of the substance. Now, specific heat we defined as the amount of energy required for a substance to change in temperature by 1 degree Celsius. Could be absorbed or released, increase or decrease, but it's the amount of energy to change the temperature of 1 gram of a substance by 1 degree. We commonly looked at specific heat measured in calories or measured in joules, and we can convert between those two. Remember, 1 calorie is equal to 4.18 joules. The larger the specific heat is, the more energy it takes to change the temperature. The lower the specific heat is, the less energy it takes to change the temperature. So in these examples, like the iron frying pan versus the earthen, what would be like a ceramic pot, The iron frying pan has a much lower specific heat, which means that it takes less energy before the temperature starts changing, where ceramic has a higher specific heat, so it requires more energy before the temperature starts changing. That's assuming that both of these are equivalent mass. Now, let's take water, right? Water in this can versus water in like the ocean, they both have the same specific heat. So then we're looking at the mass of the object. The smaller the mass, if I'm looking at or comparing substances that are the same, the smaller mass is going to heat up easier versus the larger mass, because again, that's the other variable in the equation. Assuming I'm changing the temperature by the same amount, the more mass there is, the more particles there are that have to have energy to start moving faster to heat up, or losing energy to slow down, so the more energy it's going to take, right? That should make sense. Here's some common specific heats in joules per gram degree Celsius and calories per gram degree Celsius for some common objects. We looked at the idea like if I have two blocks of metal, 50 grams of aluminum and 50 grams of copper, if both of these are absorbing the same amount of energy, then because aluminum's specific heat, I'll use joules, is 0.9 joules per gram degree Celsius, and copper's specific heat is 0.386 joules per gram degree Celsius. Because this takes less energy to change temperature, if they're both absorbing the same amount, then the copper is going to be able to undergo more temperature changes than the aluminum is. So at the end of the day, the copper is going to end up at a higher temperature than the aluminum because its specific heat is lower, and specific heat is literally measuring the amount of energy necessary to change the temperature of the substance. We look at phases of matter. We looked at this in the beginning of the year when we did matter, but reviewed these three phases. We should understand the difference on the particle level. What makes something a solid, liquid, or gas is how we define what's going on the particle level. And we should be familiar with all of the different properties, the particulate properties of solids, liquids, and gases that are presented here. We then related the two ideas we just introduced, which were phases of matter and then the heat involved in heating up or cooling a substance. We related those two ideas together to look at the heat involved in a phase change. There are 6 phase changes we should be familiar with, right? There are 3 of them that are endothermic, meaning that energy is going into the substance to cause those phase changes. That's melting, vaporization, and sublimation. And then there's 3 that are exothermic, meaning heat has to leave the substance, or heat has to be removed from the substance to cause those phase changes. That's freezing, condensation, and deposition. So we should be familiar with those 6 changes and whether or not they're endo or exothermic. And then we looked at the heat involved in those changes. Now, heat is very weird. It's tricky, and mostly because it's abstract, right, in terms of the concept of energy. But for our purposes, heat energy does one of 2 things, right, at a time. Heat energy can either change or be converted to kinetic energy, meaning it can make particles move faster or slower. That will change the temperature. Or heat energy can be converted to potential energy, and it can work on either separating particles from one another, like weakening intermolecular forces or weakening bonds, or strengthening intermolecular forces or bonds between particles to bring them closer together. But it can't really do both at the same time, and that's where we're going to leave it for our purposes. If you take higher level chemistry, you'll get into the little nuances and the differences there. For our level, heat's going to do one of those 2 things at a time. So it's either changing kinetic energy, making the particles move faster or slower, or changing potential, making the particles move further apart or closer together. And we looked at those ideas when we plotted how the temperature changes during phase changes on a heating or cooling curve. And we got this overall pattern. Now, these are both heating curves, but remember, we can have a cooling curve if we graph this the other way. If we started with a gas and then ended with a solid, I'll get rid of that for now so that we can just focus on the heating curve. If we start with a solid and we start adding heat, we add a constant amount of heat energy, it's going to make the particles move faster. Particles move faster because they have more kinetic energy. The average kinetic energy increases, and we register that as the temperature increasing. Remember, temperature is a measure of the average kinetic energy. So if the average motion of the particle starts to increase, my temperature is going to increase. But there's a point at which, even though heat is going into the substance, it's not going to make the particles move faster anymore. At that point, we transition from the kinetic energy being changed to potential energy being changed. And instead of the heat going in and making the particles move faster, the heat's going to go into potential energy and start moving the particles further apart from one another. That is when we get a phase change to occur. So during this portion, I notice that temperature is constant. That's the plateau area of that graph. Even though heat is being added, that's really important. It's not that heat's not being added there. Heat's being added, but it's not making the particles move faster. It's weakening the intermolecular forces to move the particles further apart to cause the phase change of, in this case, melting from solid to liquid. Once that entire substance melts, and I have just a liquid, then the heat transitions again. Now it's not changing potential energy anymore. It's going to go to start changing kinetic energy again. And those liquid particles are going to absorb energy, start to move faster. My temperature is going to increase until we get to this point, which is going to be the boiling point, where, again, we have a transfer. Heat's not going into or being converted to kinetic energy. It's being converted to potential. And the liquid particles, the IMFs, will start to weaken between them until they're a gas, and the particles will move far enough apart until they are in the gaseous phase. That is the phase change of vaporization or boiling. Once that's done and the liquid has completely turned into a gas, then the heat goes back into changing the kinetic energy, and then we can increase the speed of those gas particles. And then this entire section is where we picked up with chapter 10, but that will be a separate video. We looked at gases and heating a gas and cooling a gas and changing the pressure and all of that with that one phase. But again, that's for chapter 10's review video. Now, again, cooling curve, same rules apply, except we're removing heat energy, so we're either slowing down the particles or we're increasing the potential energy by strengthening the IMFs between the particles. Now, because the temperature doesn't change during these regions, we cannot use mc delta T to calculate the energy involved in the phase change. We can use mc delta T for these specific regions. So here, here, and here, we can use Q is equal to MCAT. We can use mc delta T because I have a mass of the substance. I can figure out what the specific heat is, and then I can figure out what the change in temperature is because I have a change in temperature. In these regions of the graph where temperature is not changing, this formula would be irrelevant to us because there is no change in temperature. We use these two formulas for those areas of the graph. Q is equal to MHF and MHV. It's similar, the only difference is there's no change in temperature, and HF is the heat of fusion. That's measured in joules or calories per gram, and HV is the heat of vaporization, also measured in joules or calories per gram. So the heat of fusion, for example, for water is 334 joules per gram. That means for each gram of liquid water that we want to freeze, we have to take away 334 joules of energy. For each gram of liquid water we want to melt, we have to add 334 joules of energy. The heat of fusion works for both of these phase changes, right? Because freezing and melting happen at the same point, and heat of vaporization works for both of these phase changes. Vaporization and condensation happens at the same point, happens at the same temperature, just a matter of is energy going in or are we taking energy out of the substance. The last thing that we looked at was gas pressure and vapor pressure, and this was sort of a way to wrap up chapter 9 with phases and look a little bit more at the gas phase and vapor phase, and also to introduce us and lead us into our next chapter, which was completely focused on gas law. So a couple of the things here. We focused on gas pressure. We said that pressure is not a force, but it has to do with forces. It's a force over a given area. And specifically for us, we're focused on gas pressure. We don't care about the pressure of a ball hitting a wall or the pressure of someone hitting another person. Those are more physical examples of pressure that you'll look at in physics. But in chemistry, the pressure we're concerned with is gas pressure. And gas pressure is caused from the force that a gas particle makes with the wall of the container over that specific area where the gas particle collides. So pressure, again, is a force over an area. For us, we just have to know that gas particles or gas pressure has to do with the frequency and force of the collisions that the particles are making. If I can get the particles to increase their frequency of collisions or increase the forcefulness of their collisions, I'm increasing the pressure. And if I'm decreasing the frequency and or force of the collisions, we are decreasing the pressure. Vapor pressure is the pressure exerted by vapor over a sample of a liquid. Now, again, subtle difference, but there's a difference in when we call something a gas versus vapor. When we call something a gas, that substance exists as a gas at room temperature. When I call something a vapor, that substance is in the gaseous phase, but it doesn't exist as a gas at room temperature. It exists as a liquid or solid. So when we talk about vapor pressure, we'll say, let's take water, for example. We've talked about water a lot this year. The vapor pressure of water is a liquid at room temperature normally. But some of the particles, because not all of them are moving with the same amount of speed or energy, have enough energy to turn into the gaseous phase, and they do. Gaseous water we call vapor because it typically exists as a liquid at room temperature. So vapor pressure is the pressure exerted by vapor or the gaseous molecules of a substance over the sample of a liquid. Could be over the sample of a solid, but we really focused over the sample of a liquid. Vapor pressure is completely temperature dependent. If I increase the temperature of a liquid, I'm providing more energy to all of the particles, but remember, they don't all have the same energy. There's that distribution. And I'm increasing the fraction of particles that have high enough energy to turn into vapor. So if I increase the temperature, more energy is provided to the particles, more of them have enough energy to turn it into vapor. More vapor means more collisions, and that means more pressure. We looked at vapor pressure curves and the difference between different substances. In this example, A has the higher vapor pressure at a given temperature. We should just be able to see that from the graph. That means that A has the weaker intermolecular forces. A having a higher vapor pressure means it has more of its particles, whether it's a liquid or solid, turning into a gas at a given temperature. The only way it would be able to do that to a greater extent over B is if the particles are not held as strongly together. So A has weaker intermolecular forces, B has stronger intermolecular forces. Boiling point's related to that. A has the lower boiling point. If it has weaker intermolecular forces, it more readily turns into a gas, so it's going to require a lower temperature to completely, as a whole substance, turn into a gas. Now, we looked at, one of the last things we looked at was how we define boiling, right? So it's a subtle change in the definition. Boiling to us up until this point was the phase change from liquid to gas. But boiling does not just depend on temperature, it's also pressure dependent. So boiling really is the temperature at which the vapor pressure of a liquid equals atmospheric pressure. Atmospheric pressure is pushing down on a liquid at all times. That's preventing the entire sample of a liquid from just vaporizing. So we need to build up enough vapor over that liquid so that the vapor pressure meets the atmospheric pressure, so there's no more sort of competing force that's pushing down on it. How do we increase the vapor pressure? Well, we increase the temperature. And once we increase the temperature enough so that we form enough vapor to match the atmospheric pressure, that is known as the boiling point. We know that as elevation increases, boiling point decreases because the atmospheric pressure is changing. In fact, it's decreasing. So therefore, there's less energy needed for the vapor pressure to equal the atmospheric pressure. We don't have to heat the substance to a high temperature like we would at normal atmospheric pressure at sea level for the vapor pressure to equal atmospheric pressure. If we go below sea level and the atmospheric pressure is higher, then we need to heat the substance to a higher than normal temperature to build up enough vapor so that it meets the atmospheric pressure. So boiling point actually increases when we go below sea level. The relationships that we should know are that the weaker IMFs a substance has, the higher the vapor pressure because the more readily it's turning into gas, the lower the boiling point, and that it evaporates more readily, and then vice versa. The only other thing I want to mention before we end this video is reading pressure and manometers, how we would measure gas pressure. So this example here is a barometer. A barometer specifically measures atmospheric pressure, and it's a column of mercury that's in an inverted tube in this pool, and the atmospheric pressure is pushing down on this mercury up into the tube. And we literally read how many millimeters the mercury rises. That's where the unit millimeters of mercury comes from. It's also a unit of torr, from Torricelli, the scientist who came up with the idea of the barometer. Normal atmospheric pressure is 760 millimeters of mercury, or 760 torr, or 1 atm, or 101.3 kilopascals, or 14.7 psi. We went over all those different units. If the atmospheric pressure changes, like let's say it increases, it will push more mercury up, and then the level increases, so it's going to be greater than 760. If the atmospheric pressure decreases, it can't push the mercury up as much, so it falls, and the reading would decrease. If we want to measure gas pressure, we use something called a manometer, and we really looked at open-ended manometers. So open-ended meaning the end is open to the atmospheric pressure. And reading the gas pressure is all about looking at the two competing forces, the pressure of the gas and the pressure of the atmosphere, and the level of mercury that's in the U-tube of the manometer. So the pressure of the gas is pushing in this direction, the pressure of the atmosphere is pushing in this direction. In this case, the level of mercury is equivalent, telling us that the pressure of the gas is equivalent to whatever the atmospheric pressure is. More often than not, the gas pressure is not going to be equivalent to atmospheric pressure. In this example, I can see the gas pressure is greater because the level of mercury is higher on this end and lower on this end. So it's greater than atmospheric pressure. We know if they were equal, it started out equivalent to atmospheric pressure. So all we have to do to figure out the gas pressure is start with whatever the atmospheric pressure is and add the level of mercury, the difference in height of the mercury, to the atmospheric pressure to figure out what the gas pressure is. If the levels look like this, and that's telling me the atmospheric pressure is greater because it's pushing the mercury closer to the gas side. So again, assume it started out equivalent to atmospheric pressure. All we have to do then is subtract this difference in mercury from the atmospheric pressure to figure out what the gas pressure is. We utilize all of this pressure stuff in the next chapter, which was focused on gas behavior and gas laws, but that is for another review video. This brings us to the end of Chapter 9, Physical Changes, and you should be ready to take your Chapter 9 throwback quiz.